Okay. So you want to first of all come up with a prior based on some logical reasoning, um, and sometimes that prior, as we're going to see today, might be a completely general and vague prior. The good thing about the Bayesian framework, though, is that you start with the prior, which is a belief or assumption about the nature of the parameter of interest. Okay, and then we gather data to update our belief about that parameter. And then through the mechanism of Bayes' theorem, we then update our belief about the prior, and then we get a posterior belief. We saw an example last time where we had a random sample of size 2 from the Poisson distribution, and our prior belief was that either theta was equal to 2 or equal to 3 according to this probability distribution, right? We collected our data, our random sample, x1 is equal to 2 and x2 is equal to 4. And then through the mechanism of Bayes' theorem, which is a process by which we can find these inverse probabilities, we saw that we started with a belief about theta, which is our prior belief. We updated it based on the data, and through Bayes' theorem, now we have a posterior belief about theta. Okay, so our posterior belief about theta is the belief about theta or the distribution of theta given our random sample. Okay, and we saw that the data did have a say. The nature of the data that we saw, had a pretty logical impact on the prior probabilities that we placed on theta. So any questions on that process with this example? Okay. So we kind of looked at the notation here in terms of the discrete case, which is, what this example was, a discrete case. And the interesting thing is, when we say discrete, we're talking about discrete in terms of the parameter, okay? And again, I'm monitoring the chat room, so any questions that come up, you can email the class, or sorry, chat, send a message to the class, or just DM me directly if any questions come up, okay? So this is a discrete prior, right? Because we're saying that theta can be equal to a countable number of values, 2 and 3. So that when we say discrete, we're talking about that. Usually, of course, we're talking about the x's, okay? And in this case, our x is discrete as well. But the distribution of most importance is the prior, which is discrete, okay? Alternatively, however, we could have a continuous prior, right? In which case Bayes' theorem would look like this. Okay, we have a continuous prior, then Bayes' theorem would be k of theta given x1 to xn is equal to f. Okay, now we're going to integrate over omega, the same quantity in the numerator. Okay. And we're integrating with respect to what? What should I put right there?
You're integrating with respect to x?
In this case, Jonathan, it's actually not going to be respect to x.
Theta?
Yeah, it's going to be theta. That's right.
Oh, because theta is a random variable.
Yeah, theta is a random variable. Mm-hmm. So see, like here, the only thing that varied from this expression to that expression, the only thing that's varying is theta, right? In the denominator for Bayes' theorem, the only thing that's varying is theta. And so that's what we have going on down here as well. Okay. So this is kind of the way Bayes' theorem is going to work. Okay. And let me talk about some of the notation and terminology that we use here. Okay, so obviously we know that h of theta is a prior. K of theta given x1 to xn is a posterior. And then our F or P, but I'll just write F given theta is a likelihood. Okay, we're going to obviously talk a lot about that in chapter 6, but this is what we call the likelihood. All right. If we have a random sample, then of course f of x1 to xn theta is equal to the product okay. It's also expressed as L of theta or L of x1, xn theta. Okay, various different ways we express the likelihood. Okay. Finally, this denominator. Sometimes it's expressed as we call the integral over omega of g of x d theta. Okay. And that's g1 of x, right? Because it's some function of only x. We integrate with respect to theta, so the theta gets integrated out. And it's called the marginal. Okay, so the thing that's most important about this denominator is that it is a function of the x's and not a function of theta. Okay. Okay, any questions? So it's a lot of notation, but once we start doing some examples, it'll start to feel a little bit more familiar. Okay. Okay. All right, so suppose x is a single observation from the binomial NP distribution. What are some feasible priors? Okay, so in other words, we know that x tilde binomial NP. So P sub x is n choose x, P to the x, 1 minus P to n minus x. Okay, so that's going to be our observation distribution. And in fact, that's going to be our likelihood. We only have one observation from the binomial. Okay, so one instance of flipping a coin 10 times and observing how many heads we got. Okay, and we want to make inference for the value of P, right? So frequentist perspective would be, okay, well, let me just look at my 10 tosses and I got 7 of my tosses being heads. So my P hat would be 7 out of 10, right? And then I can maybe create a Combs interval, et cetera, okay? But the Bayesian perspective instead says, no, let me actually enter into my inference. And before I even flip the coin one time, I'm gonna have some kind of assumption, some kind of belief about the value of P, okay? And come into it with that. Then I'm gonna flip the coins, use the flips to update my belief and come up with a new set of beliefs about the value of P, okay, and the distribution of P. So that being said, we want to go ahead and determine, well, what are some reasonable beliefs we could have about P? What are some reasonable prior distributions we can have about P, okay? The key characteristic of P that helps you determine what some feasible priors could be is the support. Or I should, so here we go with a little bit of equivocation, right? The support of P, right? Which we never talked about before, so I was a support of X. But if you think about P as a random variable, then P has a support, and that support is what we used to call its parameter space, and we'll still call it that, right? So we know that omega in this case for P is equal to that, okay? Right, so that being said, what do you think are some distributions for P that would make sense, given that P lives between 0 and 1?
Would uniform be one?
Uniform, okay. So yeah, P could be uniform.
Standard normal?
Feasible priors. So let me write down what everyone is saying. Okay, what else? Any other feasible priors?
Just normal. Normal.
No. Mm-hmm.
But all those has like a domain from negative infinity to infinity though, right?
Ah, okay. So yeah, thinking about the domain, right? Yeah, that's the thing. So when we think about the prior for P, what we're saying is now on my x-axis is P, right? And I want to look at a PDF on certain values of P. So a probability density for various values of P, knowing that P lives between 0 and 1, right? So because of that, the normals wouldn't necessarily make sense, you know, unless if we did like we had on midterm 1, like a truncated normal or something. But the normal in general wouldn't make sense because the normal lives on the whole real line. Does that make sense? So yeah, Derek, you're right. We ideally want distributions that live between 0 and 1. So uniform could work because I could just say, well, uniform on 0, 1, that's a feasible distribution, okay? Okay, David, I see is saying Bernoulli. So Bernoulli, Bernoulli P would not be feasible because Bernoulli is discrete, you know? Whereas if I look at this parameter space, it's not like the Poisson example where we said theta is equal to 2 or theta is equal to 3, right? That's a discrete parameter space. And that's a case where the Bernoulli might work. But in this case, our parameter space is continuous, right? So we need a continuous distribution. So that's a good point, okay? I'm still thinking about one more. The uniform is definitely a good possibility. What else? Exponential, beta.
A beta?
Beta. Okay, so exponential, remember exponential is this. So it lives from 0 all the way to positive infinity, right? So again, unless we truncated it, which we could, then exponential wouldn't be feasible because it's giving non-zero probability to values that we know are impossible, right? Values bigger than 1. Okay, so beta makes sense though. Beta makes sense because we know for the beta distribution, the support is between 0 and 1, right? For the beta, okay? So yeah, the beta and the binomial are gonna work well together as well as the uniform. And you may recall, we spoke about this a couple of weeks ago that the uniform actually is just a special case of the beta distribution, right?
Oh, can we say gamma? Because these are all belong to gamma.
Say that one more time.
Can we say gamma? Gamma
So-
distribution? Because these two are belong to gamma, right?
But the problem is, so they're related to gamma.
Okay, related to.
They're related, but the gamma also has a support of the whole real line, right? So we don't want that. In other words, we're working backwards, and I say, I want this to be the support. Then we say, okay, which distributions have this support between 0 and 1? And of what we've looked at so far, really, it's only uniform and beta. Nothing else has a support between 0 and 1. Okay.
Okay.
But then if you think about the homework problem, when you're looking at the sigma as your parameter, we know that sigma has a support of, just being non-negative. The support of sigma is all positive numbers, right? The support of sigma is positive numbers. That's why the gamma makes sense for the sigma, because same support, right? The same support, all positive numbers, okay? Since sigma is positive. Okay? All right. Okay, so let's see if we can look at both of these. First, we'll take a look at the uniform distribution, uniform prior. Okay, so suppose h of p is 1 for 0 less than p less than 1 and 0 else. Okay, so we want to go ahead and find the posterior. That's going to be p of x given p, h of p, divided by probability x given p, h of p. Okay. And of course, this p is a different p than the one inside the parentheses, right? That capital P is the PDF P. Okay, so what am I missing from the denominator?
Integral. No.
Integral? Integral? Or is it summation? Integral or summation?
Wait, why would it be a summation if the uniform's continuous?
Oh, I never said it was a summation. Yeah, I'm asking. Is it an integral or a summation? Are we sure? What do we, I want an exclamation point, not a question mark. Is it an integral or a summation?
It's a summation. By that definition, it would be a summation since it is a continuous function.
Summation? Jonathan, was that you, Jonathan? The summation? Well, it actually would be an integral. Okay. And we're going to be integrating from 0 to 1. Okay. Again, how do I know what it's going to be? Here, it was a summation because my theta could only be 2 things. Theta was discrete. 1, 2. I can count how many things theta can be, right? Discrete. In this case, how many things can P be? How many different possibilities are there for the value of P? I can't count. It's continuous, right? So that's what we're integrating. Okay, so this is going to end up being the PDF Let me write this. Okay, multiplied by the prior divided by the integral. And let me just bring this out. Any questions? Okay, those are going to cancel. And for the denominator, okay, let's actually go here. Okay, for the denominator, I want to integrate that, okay, with respect to p. Okay, so think this. Think this. Okay, I'm going to say, let's say that's y to the x, 1 minus y to the n minus x dy. Okay, if you wanted to integrate that, what would you do?
Use substitution.
U sub? Now, if you did a U sub, it's going to be tricky because you don't know what x is. You know, if these were finite numbers, then the U sub, you know, might work, but you don't necessarily know what these numbers are, right?
So then integration by parts.
Integration by parts, the same thing, Jonathan, because it's like, well, how many times we do integration by parts, right? As long as you don't know what those exponents are as in terms of actual numbers, then you're kind of stuck. I see Renee is saying gamma in the chat room. You're close. It's the same idea in terms of what we did with the gamma. If I had an integral like, you know, x to the 12th e to the minus 7 x dx, we could integrate that without integrating, right, by using the gamma distribution, okay? But it needs to be in this format, okay? But since it's in this format, what are we going to do instead?
We're gonna like finagle it somehow and make it that form.
This form up here?
No, wait, yeah. No.
No, that e is going to be hard to get.
Oh, okay.
Yeah, yeah, we can't get that e. But what if we use the beta distribution instead? So recall that y to the alpha minus 1, 1 minus y to the beta minus 1 dy equals 1. So it's similar to the gamma trick that we do from time to time, but we're just going to do it with the beta instead. Okay. So if I can just figure out the correct value of alpha, the correct value of beta, then this looks like a beta integral, right? It looks like a beta integral, and I can just work with the constants to make it work. Any questions? Okay. So if we do that, then this kind of looks like we have a beta distribution with what values for our parameters. So what would the alpha be?
X plus 1, right?
Yep. And then beta n minus x plus 1. That makes sense? Any questions? Okay, so because of that, what I could do is just try to see if I could figure this out and get my integral without having to do the work, okay? Okay, so let's proceed. This is going to be equal to p to the x, 1 minus p to the n minus x over. Okay, so what do we need? We need, on the inside, gamma of alpha plus beta. Which is going to give us n plus 2, gamma of alpha, gamma of beta, okay? And so we'll flip that, or actually, instead of flipping it, let me just put it up here. Okay, so same quantity above and below. And then I'll have my p to the x, 1 minus p to the n minus x, dp, 0 to 1. Okay, any questions? All right, so that means my denominator is 1. And we end up with this solution. Okay, i.e., p is beta x plus 1, n minus x plus 1. Okay, and actually, sorry, it's really this, p given the data, the posterior. Okay, any questions?
Can you scroll up a little?
Yes.
I got a quick question.
Yes, Dean.
Why is it important to note that it's p given x is distributed that way? Like what was the significance of that change from before?
Yeah, so the P without the condition is our prior belief, uninformed by the data we've observed. But once we observe the data, then we have to put the given X, and then that's our posterior belief.
Got it.
Yeah. Okay. All right, so our prior was here, and that's beta 1, 1. Okay, uniform is beta 1, 1. And then we observed the data X. Okay, this was our data that we observed. And now our posterior is beta x plus 1, n minus x plus 1. Okay. Okay. So that's kind of the process of finding a posterior using Bayes' theorem. Okay, now something that hopefully you'll see is that really the only thing that mattered in terms of you know, the functional form of our answer was the fact that the numerator looked like this. Okay, the numerator had you know, this component to it. So just by looking at that numerator, we could actually tell, you know, even more importantly than the denominator, looking at the numerator, we could tell that our answer was going to be some kind of beta, and more precisely that it needed to be this beta, right? Notice how this fact we stated about the denominator is actually what ended up being our final answer about the numerator, okay? Moreover, as we stated earlier, the denominator is never going to depend on P. We're integrating out the P, okay? So the denominator will never depend on P. It's just going to be a constant relative to our variable of our random variable, which is P. So the question is, what constant is the denominator going to be? And this answers that question for us. The constant that the denominator will be is always going to be the constant that we need to make the numerator a PDF, right? The posterior is a posterior distribution. So the posterior is a PDF or a PMF, as the case may be. So therefore, if you think about it, you don't really have to we didn't have to do this. We didn't have to integrate the denominator, because the denominator is what it must be to make the numerator a PDF. So if we have a numerator, and so using Bayes' theorem, the numerator looks like this, or it looks like this. If we can take a look at our numerator and the functional form of our numerator looks familiar, then all we really need to do is manipulate it and figure out what constant will make that numerator a PDF, right? And then once we find that constant, we found our posterior. Okay, so in other words, what I'm really trying to say is, you don't have to find the sum step by step. You don't have to find this integral step by step, because it's always going to be the constant that you need it to be to normalize the numerator. Okay, and so because of that, really, you know, what Bayes' theorem is kind of remembered by in terms of a way to remember what is going on and how it works and what it's doing, is that the posterior is proportional to the likelihood times the prior. Okay, so this is kind of the golden rule in terms of Bayes, you know, Bayesian statistics. That's how you get from the posterior to the prior, by remembering that the posterior is proportional to the likelihood times the prior. And you don't necessarily have to worry about finding that denominator, because it's just a proportionality constant. It is the only proportionality constant that makes the numerator a PDF. Sometimes it's written this way, so the symbol for is proportional to is something like that. Okay, so the posterior is proportional to the likelihood times, actually, let me write it with the x's just to make it clear, times the prior. Okay. All right, so that's Bayes' theorem right there. Okay, any questions?
Yeah, I'm sorry. Is it proportional or inversely proportional?
Proportional to.
Oh, okay.
Because this numerator here is the likelihood times the prior.
Right.
Yeah.
Okay.
Okay. I should have put more space here, but let's see what we can do. Okay. So because we mentioned that the uniform was a feasible prior, and then also that the beta was a feasible prior. Okay. So now let's suppose we have a beta prior. Okay, so suppose our prior is a beta prior. Gamma of alpha plus beta, gamma of alpha, gamma of beta, p to the alpha minus 1, 1 minus p to the beta minus 1. Okay. In other words, p is beta, alpha, beta. Okay. The same context, we have one observation from the binomial distribution. Okay. And now we have the a beta prior. Okay. Okay, so we're going to go through this same process, except instead of having a 1 up here, now we're going to have this up there. Okay, that's going to be what we put up there. Okay, so you can see that if you have this prior in the place of this 1, okay, there's going to be a lot of terms up there, but the good news is that there's a lot of like terms, common bases, and you can combine the p's, combine the 1 minus p's, okay? So in other words, what we'll get is it's proportional to, okay, p to the, let's go ahead and put the x first, x plus alpha minus 1, 1 minus p, n minus x plus beta minus 1, okay? That's it. Okay, I'm just dropping every other term from this entire Bayes theorem expression that we see up here. Okay.
Dr. Suaray,
Yep.
the one with the green text right above the one you just wrote down, that's 1 minus p to what power?
Beta minus 1.
Beta minus 1. Okay, thank you.
Okay. So I'm basically doing the same things we did for the previous problem, except now my prior looks like this quantity instead of just a 1. So if I replace this 1 with this quantity and I multiply, I'm going to get a whole bunch of stuff, but I'm going to have p to this power, 1 minus p to this power, okay? I'm going to divide that by an integral, but I already know that that integral is just going to be a number. So when we're doing Bayes theorem, all we're concerned about is our parameter and the functional form of that parameter, okay? Okay. Any questions? Okay, so what that is going to do is going to lead to the fact that our posterior is also going to be beta. Okay, x plus alpha and n minus x plus beta. Okay, you can see that this case above is just a special case of that with alpha equals 1 and beta is equal to 1, which would be the uniform case. Okay. Okay. So I know that right now this kind of seems out there, just a lot of calculations without necessarily any relationship to reality or real data. Okay. But are there any questions before I proceed? Any questions? Okay, I want to run through a couple of simulations just to kind of illustrate what is really going on with this. Hopefully that'll bring a little bit more intuition in terms of what this process entails. So as I'm kind of shifting over, and I'll come back to these notes, but let me shift over to R right now. As I'm shifting over, is there, or I guess I received an email that some of you guys may be having or may not be able to access the notes or the lectures, the online lectures through your single sign-on. So has anyone had any success accessing the lectures through the single sign-on? Has anyone had any success? Okay, John says he hasn't been able to access them. Okay, so I guess what happens is when they're recorded, they're saved, and I guess maybe they're just saved to my single sign-on, not to yours. So because no one is saying that they've received anything. So okay, so that means I have to find a way to deploy them to you, and I'll go ahead and do that one way or the other. I'll let you know over the next couple of days. Okay. Okay, so are you guys able to see my R Studio right now?
I don't see it right now.
No? Okay.
There we go.
Okay, thank you. Thank you. So this is just a quick little program that is going to do the following, okay? So let me use 10 as my n, okay, and 0.7. Okay, so we know, so here's the, P is the true value of our parameter, and 10 is our sample size. So when I flip a coin 10 times, the true probability of heads is 70%. But of course, when I flip a coin 10 times, even though the true P is 70%, I could see 6 Ps, I could see 1 P, I could see 10 Ps. That's why it's a random variable, right? So I'm gonna have one instance of that. And then in addition, I'm gonna have my prior to be a uniform prior, okay? So what this is gonna illustrate is the impact that the data has on my prior belief, okay? All right, so in this case, what happened was our observed proportion was 50%, okay? So we saw 5 heads in our 10 tosses. The red horizontal line, of course, is our uniform prior. And then the blue or the teal distribution here is our posterior based on this vertical line, which is our observed data, okay? So our initial belief was basically uniform. In other words, what I'm saying is I don't have any strong inkling towards smaller values of P or bigger values of P. I'm kind of ambivalent, right? In terms of any value of P is equally likely in terms of my prior belief. If that's my prior belief I'm bringing to the table, then the data is going to have a really strong impact in terms of my posterior belief, because I've observed this 50%, and now you can see we have a distribution that is, in this case, symmetric, but the mode is at 50%. The height of my belief is now what I observed. Okay, so that's a very powerful illustration of the fact that the Bayesian estimation principle is highly dependent on data. So even though you may come into it with a strong belief, the data still has a very powerful impact in terms of your updated belief. Okay, now let's say we have alpha is equal to 3. Okay, so this is going to be a skewed distribution, right? So now our prior belief is going to be this red. And so what we're saying is we have a stronger belief that P is a big value versus P is a small value, okay? That's our prior belief. We did our experiment and we got a P hat value of 80%, okay? Which reinforced that belief, And so our posterior mean is still kind of in line with that skewed left nature, but now it's shifting more towards the data. So it's still skewed in the same way, but it's shifted towards the data, okay? Let's do one last one with distribution where we believe that P is small. We have stronger belief that P is small, okay? So here our prior, the red curve is we really believe that P is a small value. The probability of success is small. However, we did our trial, and again, we got an 80% observed probability of success. What that's going to do about our belief is it's going to shift it again towards the data. And now we have, just based on that one observation from this binomial distribution, we went from a skewed right prior to a skewed left posterior. Okay, so the data has a very strong impact on our beliefs. All right, any questions? Okay. Okay. Prior distribution is said to be a conjugate prior for an observation distribution when it has the same functional form as the likelihood. Okay, so this leads to posteriors that can be found without integration. All right, so this is exactly what we experienced with the beta and the binomial. Okay. All right. This only holds true for members of the so-called exponential family of distributions. Okay, so the exponential family of distributions is going to be an extremely important concept when we go into chapter 7 and chapter 8 with sufficiency. But let me just write down the general format of the exponential family of distributions. And of course, we'll talk about it in a lot more detail in the later chapters. But the exponential family of distributions is if I can write my PDF in this format. For X in the support and 0 otherwise. Okay, then we have a PDF that's a member of the so-called exponential family distributions. Okay, so it turns out that the binomial is a member of this family, right? Even though there's no E in the binomial distribution, I can write any number as E, right? I can write 7 as E to something, right? So the binomial is a member of this family of distributions. So is the beta, and they're conjugate to each other because they have the same functional form. Okay, it's something that you may have actually noticed on your own, that you look at the binomial, look at the beta, they kind of look the same, right? And because of that, they're what we call conjugate distributions, okay? They're a conjugate pair. Same thing with gamma and Poisson. So our gamma and Poisson distributions are a conjugate pair. Okay, so let's think about how the conjugation works. Because when we talk about a conjugate distribution with the beta and the binomial, one of them was the prior distribution, the other one was the likelihood. Okay, right? So one was prior and one was the likelihood. We're talking about the gamma and the Poisson. Which one would be the prior? Which one would be the likelihood? In other words, which one would be the observation or the data distribution? Which one would be the distribution of the parameter? Okay, and to answer that question, you have to think about parameter space. You have to think about support. I know that Poisson is discrete. So the question is, are the parameters of the gamma, do they live in a discrete space, right? And of course, we know they don't. On the other hand, I know that the gamma is a continuous distribution. So I ask myself, does the parameter of the Poisson live in a continuous space? And the answer is yes, it does. For the Poisson, we say P sub x is e to the minus lambda, lambda to the x over x factorial for lambda bigger than 0, right? So this is our omega. And omega is a continuous parameter space that lives on the positive half of the real line. But it just so happens that that is the support of the gamma distribution, right? So for the gamma, then our h of lambda, our prior, okay, is going to be 1 over gamma of alpha, beta to the alpha, okay? Our variable, which is going to be lambda, the alpha minus 1, e to the minus lambda over beta for lambda bigger than 0, okay? All right, so our prior, our data, okay? And then our posterior, something that you can figure out on your own time. But the key thing that we're illustrating in this definition is the idea of conjugates. Look at the functional form, okay? If you look at this, e to the power, lambda to a power, we have the same thing here. E to the power, lambda to the power. So these are a conjugate pair, okay? Any questions? Okay. Okay, Bayesian inference. Estimation and testing of a parameter theta characterizing the observation distribution is based on results obtained from the posterior, okay? The Bayesian estimation principle is that the parameters of the posterior are the estimates for the parameters of the observation distribution, okay? All right, and so I see a question, how do we determine whether the gamma is prior or not? So for that situation, it's based on the support, okay? Could the Poisson be the prior of the gamma? No, because the parameters of the gamma are not discrete. Could the gamma be the prior for the Poisson? Yes, because the parameter for the Poisson is continuous. Okay, so that's kind of how you can determine some feasible priors. All right, so this Bayesian inference principle is the following. Once we find the posterior distribution, okay, this posterior distribution is it's the sum total of how we do inference about the parameter of interest, okay? So the way that I'm going to do Calm's intervals or hypothesis tests or point estimation for P in this context is going to be based on this posterior distribution, right? Because I've seen my data, I've updated my belief, now I'm ready to make some statements about my parameter. Okay, so the quickest way of seeing that is in terms of the idea of finding a point estimate in the binomial beta situation, okay? All right, so if P, the prior, is beta, alpha beta, okay, that leads to P given X being beta alpha plus x, n minus beta plus x, right? Okay. Using MSE as our error criterion. Squared error loss, as it's called sometimes. The parameter of the posterior or the prior rather, posterior that is optimal for estimating P is expected value. Okay, so the expected value. The expected value of the posterior, as you may recall for the beta, it's in general, it's alpha over alpha plus beta is the mean of the beta distribution. So in this case, it would be alpha plus x over alpha plus x plus n minus beta plus x. Okay, so our point estimator for the for P is just going to be this value right here, the average or the mean, the expected value of our posterior distribution. Okay. All right, any questions? Okay. Okay, notice.
Doctors,
Question?
yeah. What happened to the x's in the denominator?
I think I didn't write something correctly because we should have a minus x and a plus x. I think that's alpha, let's see. Yeah, n minus x on the beta. That should be a minus, good catch.
And plus beta.
Plus beta, yeah, I swapped them. Plus beta minus x, yeah. Thanks, guys. So yeah, minus x and plus x are going to cancel each other out. Okay. Okay. So let's talk briefly about how we do inference in the case where we have normal data. Okay. So suppose we have a random sample from a normal distribution. Okay. We saw earlier the case of using a uniform prior. Okay. If you want to make inference about the mean, however, we know that for the normal distribution, it's that. Okay, so if we want to have a uniform prior for the mean, then that's a little bit unorthodox because the uniform distribution has to live on a finite region, right? But there's a way that we can kind of get around this. The nice thing about having a uniform prior is because if I don't have any strong belief in any specific zone of my parameter space, I'm coming in completely blind in terms of reasonable values for my parameter, then the uniform prior makes sense. okay? You know, however, in the case where we have a parameter that could be you know, an infinite number of values, technically you can't have a uniform PDF that's going to integrate out to one, right? I can't have a flat PDF that will integrate to one. Okay, so because of that, we know that the support must be this, as above, right? Okay. So that's going to cause us to invoke a new definition, right? And that definition is a definition of an improper prior. Our improper prior is going to be h of mu equals 1 for negative infinity less than mu less than infinity. Okay. So that's improper because, of course, that doesn't integrate out to 1. But it has a characteristic that we want of being flat. And as it turns out, that's still going to lead to a proper posterior. Okay, so the integral of the posterior will be 1. So we're good. Okay, so this is something that's frequently done in Bayesian stats, is that let's just go ahead and use a prior that's improper, because we're still going to get the benefits of you know, a context where we don't impose strong belief when we don't have strong belief, and we'll end up with a proper posterior at the end of the day anyway. Okay, so any questions on that?
Can you explain how does that 1 come from?
1 is just a constant, you know, it could be any constant, but it's just analogous to what we did up here with this 1 up here. You know,
Oh, okay.
yeah, this flat PDF. Okay. Okay. So let's see what our posterior would look like in this case. Okay. Okay, so it may feel like cheating, but you know, the fact is, even though Bayes' theorem is a fraction, we know that the denominator is a constant, and we already know what constant it's going to be. So all I need to do is write my likelihood times my prior. Okay. Because it is what we're working with. Since we have random sample, we can just take the product. And from your previous class, this should be something that you remember doing before. It's going to be something that we're going to be doing next week as well. Well, the week after. I think on Tuesday, I'm just going to conclude this Bayesian stuff and spend the rest of the time in review. And I'll talk about that in about 5 minutes. So that's our likelihood. Take the product. Okay. And that's going to be that product. Okay. Okay, so here's where you got to kind of have a mental shift. And what you have to think is, so this is my, my posterior is going to be, and I flipped it. I'm sorry, I flipped it up here. The mu has to go first. The posterior is proportional to this. Okay, the posterior is proportional to this. Okay, now the posterior is a function of mu. So I have to look at this expression and think of it as a function of mu. And possibly think about one of the PDFs, that I'm familiar with that this looks like, right? That's what we did for the beta binomial situation. So is there a PDF that we're familiar with that looks like? Okay, as a function of mu. Okay, so to get that, what we want to do first is actually let's kind of simplify that expression in the summation first. Okay, x sub I squared minus 2 x sub I mu plus mu squared. Okay, we've done this a number of times, and this is not the last time we're going to be doing it. Keep forgetting that n. Okay, so 2n x bar plus n mu squared, right? Because I'm bringing that summation inside, and we know that the 1 over n times the sum of the xi's is the definition of x bar. So that's how we get this. Okay, any questions? Okay, now this is gonna not feel right as math people, but it's completely legit when we're looking to discover our posterior. Okay, I just completely dropped this first part, right? Why is it irrelevant?
Because that just makes up like the proportional aspect of it.
Yeah, that's right, Dean. Yeah, it just makes up the proportion, the normalizing constant, and it doesn't have any mu's in it. So again, we're just trying to discover the functional relationship in terms of mu, right? Yeah, Kevin said it's just fluff. Yeah, that's fine. So really all I need is this stuff in here, right? So I can say this is times n mu squared minus 2 x bar mu. Okay. I pulled out the n, and I dropped this term, right? Again, no mu's, so it's not going to have any impact. It's just a constant, right? Anything that's not a mu is just a constant to me. I've stored away. Okay. So this expression, and I can't forget my negative, I can think of it like this. Okay. Mu squared minus 2 x bar mu plus x bar squared and do another proportionality thing. This is this. Okay. So our posterior is proportional to this, and we identify that to say that is equal to 1 over radical 2 pi sigma over radical n e to the minus 1 over 2 sigma squared over n mu minus x bar squared, i.e. normal with mean x bar and standard deviation or variance based on this. Okay. Sigma squared over n. It's going to be our posterior. Okay. Okay, so I'll pick up from there next time. And as I was stating earlier, so the exam is going to be up to what we've done today. I'll spend maybe about half an hour at most completing this stuff. And then the remainder of class, I'll devote it to any questions and give me more guidance in terms of what to expect on the exam. There are 2 practice exams that are up on Beachboard. However, maximum likelihood is not on the exam. Okay, so MLE is not on midterm 2, given the circumstances of this semester. So, you can just pretty much look at everything else that's not an MLE problem, okay? But just be careful because some problems, part A might be an MLE, but part B isn't. So anything, any part of a problem that's not an MLE is fair game and good practice, and definitely try to work on those green questions on that as well as the homework on Tuesday, okay? All right, so that's about it. I'll stick around if you have more questions. Have a good weekend. Stay safe.
Dr. Suaray, can you go to the left, please?
Like that? Or that way?
Sorry, yeah, thank you. Dr. Sorry, I have a question, not about this specific topic, but just in general, previous lecture notes. For your notation of convergence in probability and convergence in distribution, can you clarify the notation for that? I feel like it's the exact same thing. Is it?
Okay. Oh, I think it might be the way that I write my my letters. So like convergence in distribution, X bar converges in probability first, let's say, to mu would be that, right?
Okay.
And then we would say a variable xn converges in distribution to, let's say, an x, which is some distribution, something like that.
Okay.
Yeah, so that's a P and that's a D.
Okay.
Yeah.
Got confused.
Was that the issue?
Yeah, that's what I was a bit confused. But in general, even on the X, so when it's probability, we're talking about the mean, and then for distribution, we're talking about the sequence.
No, even here, I mean, like, so I think the book, a lot of times they put X bar with an N, even here,
Okay.
And here you could just say X bar and not even put the N, and have something, whatever, right? Something like that,
Okay.
So Yeah, it's sometimes the n is there, sometimes it's not. It doesn't need to be there because we all know that x bar is a function of n and depends on n. Sometimes the book just likes to put the n there to make it explicit that, you know, n is really the thing that's going to infinity and it's based on our sample size.
Perfect. Follow-up question to that discussion. For it to be considered an estimator, does all three functions need to be considered? So if it fails, for example, biasy, would then that dictate that it's not a good estimator?
So bias,
Consistency, and I think it was convergence.
Convergence and distribution. So that's a good question. No, you can still have a good estimator. I mean, it really, and because remember, good is always a relative term. It's like the Mustang versus the Prius, you know? And so it really depends on your goal in estimation. But ideally, you want an estimator that at least asymptotically with all of these. Like for a small sample size, it may not be biased, but at least if it should be asymptotically biased, right? At least for our purposes. So in other contexts, it might be good to have a biased estimator, you know, but we're not gonna worry about that. In our context, we want to have estimators that if they're not biased, then at least asymptotic. If they're not unbiased, rather, at least asymptotically unbiased.
Okay.
If that makes sense.
Yeah. So in our notes, I'm rewriting it. You gave us an example where you asked us to, I'm assuming, you know, for ourselves to try to show that, for example, that p squared is an S.
Jonathan? Uh-oh. Where'd you go? Oh. Okay.
Don't forget to stop the recording.
Thank you.
Yeah.
You.